When it comes to the science of cosmology, one of the crowning achievements of the past 100 years is the development of a standard model of cosmology. The dominant factor in determining how the universe evolves is gravitation, which is governed by general relativity and accounts for the expanding universe as well as the assembly of large-scale cosmic structures. The contents of the universe have been determined to be dark energy, dark matter, normal matter, neutrinos, and photons. And the universe as we know it began some 13.8 billion years ago, with an event known as the Hot Big Bang, with density imperfections seeded by a preceding phase known as cosmic inflation. Despite all the observational evidence we have supporting this picture, it may not be fully correct. Each time we observe the universe in a new way, we have to check that what we're seeing is still consistent with this model. With the addition of James Webb to the arsenal of tools astronomers have, is this picture in trouble? The answer would seem to be yes. So, is it time to dethrone the Big Bang Theory? Well, this topic remains controversial among scientists, as some think we need to rewrite all the textbooks while others think that our current model just needs some updates as it had been. So, who's right? All this and more will be discussed in today's episode. The first thing we have to do is lay out how we expect events to unfold in our universe based on our current picture of the universe. This picture, sometimes called the Standard Model of Cosmology, sometimes called the Inflationary Hot Big Bang, and sometimes called Lambda Cold Dark Matter, or LCDM model, has been remarkably successful explaining features ranging from the internal motions of individual galaxies, the motions of galaxies relative to one another, the motions of galaxies within groups and clusters of galaxies, weak and strong gravitational lensing on all cosmic scales, the structure and growth of the cosmic web, and the features found in the Big Bang's leftover glow, the cosmic microwave background. It also predicts that, as we look farther and farther back in time, that is, to greater and greater cosmic distances, that the galaxies we see will be inherently smaller, bluer, less evolved, less rich in heavy elements, and that at some point beyond where we've been able to look, we should cease to see stars or galaxies of any type, as we'll reach the universe's dark ages. But that's simply a picture of what happens. What we need, if we want to compare theory to observations, is to quantitatively figure out not just what happens, but when it happens, and quantitatively, how much it happens by. Even though the laws of physics are well known, and the starting point, or our initial conditions, are also well known, our best quantitative predictions still come along with a large amount of uncertainty. From the theory of cosmic inflation and the patterns of fluctuations that we see in the cosmic microwave background, we know that our universe began at the start of the Hot Big Bang, from an almost perfectly uniform state. There were the seeds of structure, density imperfections, imprinted atop that near-uniform background, leading to underdensities and overdensities at about the 1 part in 30,000 level, that were almost but not quite the same on all cosmic scales, about 3% larger on size of the universe scales than on size of a galaxy scales. We know that early on these imperfections grew gravitationally, but also had to contend with interactions with and pressure from radiation, like photons, creating a pattern of peaks and valleys in how overdense, underdense various regions were on a variety of cosmic scales. Then, the universe forms neutral atoms about 380,000 years after the Hot Big Bang, and expands, cools, and gravitates according to the laws of general relativity. As long as these density imperfections remain small compared to the average density of the universe, it's easy and straightforward to compute how they grow. But as they grow larger, a series of effects all come into play, making the question of how big do they grow and how quickly very assumption-dependent. For example, as large amounts of gas begin to accrue in these overdense regions, how efficiently does that gas cool? As these overdense regions grow within the expanding universe, with some small-scale regions superimposed atop larger-scale overdensities. How do these high-density regions interact in these overlapping locations? Some overdense regions will occur close to other overdense regions. How is the growth of structure affected when these regions interact? As normal matter accumulates in the centers of these overdense regions, it slows down, collides, and heats up. As that heat gets radiated away, how does that feedback affect the growth rate of these regions, including both the normal matter and the dark matter? And finally, when stars finally form in these very different environments to the ones we find today, how long do they live? How do they die? How does that impact the normal and dark matter that doesn't become stars? And what implications does that have for subsequent generations of stars and the growth of these early cosmic structures? It's important to understand that the answers to all of these questions are uncertain. They're firmly in the realm of the purely theoretical and are dependent on what details we include and exclude in our models and simulations. Are we using the correct models to identify halos, where a halo represents an individual overdensity in space? Or are we incorrectly treating interdependent halos as independent entities or vice versa? Are we modeling the first stars correctly, including their initial mass functions and their death throes? Or are they heavier and more likely to directly collapse to black holes than we think? For that matter, do we even need stars to form black holes? Or can these intersecting, inflowing streams of gas form the seeds of supermassive black holes directly, possibly with masses that are 10,000 plus times the mass of our sun right away? It's pretty clear that the very first objects, stars, black holes, and star clusters, begin forming no later than about 150 million years after the Big Bang, and perhaps as early as only 50 to 100 million years after the Big Bang. But these ought to be relatively rare occurrences. Bright, evolved galaxies we should see at slightly later times, like 200, 300, or 400 million years after the Big Bang, is a much murkier question. But we don't simply have our theoretical expectations, even with the appropriate uncertainties, to work off of. For the first time, owing to the unprecedented capabilities of the James Webb Space Telescope, we're beginning to discover and characterize galaxies found in these very, very early stages of our cosmic history. Scientists expected this observation find some small blue baby galaxies at early times, objects which have just recently formed out of the primordial cosmic soup and are themselves building their early stars and structures. However, contrary to all expectations, right from the very first images sent back by the James Webb Telescope, we are already confronted with galactic behemoths, giants that simply could not have formed in the time allotted to them in the established theory of the Big Bang. According to preliminary analysis, these galaxies formed just 300 million years after the Big Bang. By comparison, our planet is 4.5 billion years old, and it takes 200 million years for our galaxy, the Milky Way, to complete just one rotation. The classical theory of galaxy development cannot explain how these galaxies might have formed in such a short time. And this is just the beginning. Astronomers have always thought that galaxies couldn't have gotten very big so early in the universe's history, and would start bulking up on stars about 500 million years out from the Big Bang. But Webb galaxies are extremely luminous, suggesting that it holds an abundance of stars, which together are 1 billion times as massive as our Sun. In other words, the most massive galaxies in our sample are estimated to have masses 2 to 4 times lower than that of our own Milky Way. This was astounding. We're finding galaxy candidates as massive as our own galaxy when the universe was 3% of its current age. What's notably, it isn't just the size of these galaxies that poses a problem to the established theory. So too does their composition. The stuff they are made of typically suggests it has been recycled over many generations of star formation. Big Bang theorists calculate that after the initial explosion that created the universe, all that existed was hydrogen and helium and tiny amounts of heavier elements. In other words, Such young galaxies are dust-poor. However, we already find around 20% of the galaxies that assembled during this early epoch are already very dusty, and a significant fraction of the ultraviolet light from newborn stars is already hidden by this dust. That, put simply, broke the Big Bang model of cosmology. But the question of galaxy formation, enormous agglomerations of swirling gas, dust, and stars, is only the tip of the iceberg. Observational astronomy has uncovered far, far larger structures that completely confound Big Bang cosmologists. According to the assumptions that form part of Big Bang cosmology, no cosmic object can be more than 250 million light-years wide. And yet every year, astronomers are discovering larger and larger megastructures that are billions of light-years wide. For instance, early this year, scientists have spotted a second ultra-large structure dubbed the Big Ring that challenged long-held assumptions about the universe's structure. Situated 9.2 billion light-years away from Earth, the Big Ring is also creating problems for the current understanding of the basic principles of cosmology. The colossal structure boasts a diameter of about 1.3 billion light-years and a circumference of nearly 4 billion light-years. To put its enormity into perspective, if visible, the Big Ring would span an area of the sky equivalent to 15 full moons. And of course, this is not our first discovery of a massive cosmic mystery. 2 years prior, we discovered the Giant Arc, another megastructure measuring 3.3 billion light-years across. Both the Big Ring and the Giant Arc reside in the same cosmic neighborhood, observed at an identical distance and era in the universe's timeline, merely 12 degrees apart in the sky. But neither of these two ultra-large structures is easy to explain in our current understanding of the universe. Their ultra-large sizes, distinctive shapes, and cosmological proximity must surely be telling us something important. But what exactly? We just don't know. Regardless, there is no doubt that James Webb will continue to discover other mammoth structures, and perhaps some that loom even larger than the Giant Arc. Light itself would take billions of years to traverse such a structure. The freefall collapse of matter under gravity would have taken eons. These discoveries are weighing down on the Big Bang theory. There is only so long that the theory's defenders can continue moving the goalposts in the manner that they have done for decades to force observations to fit their preconceived view. Genuine science progresses as theories are devised to explain our observations. An accumulation of inexplicable observations at a certain stage demands the revision of a theory. Certainly, there is a disconcerted mood among astronomers. "Panic," reads the title of one pre-publication paper. Alison Kirkpatrick of the University of Kansas tweeted, "Right now, I find myself lying awake at 3 in the morning and wondering if everything I've done is wrong." However, the consciousness of the elites of the scientific community is quite conservative. Therefore, rather than question the underlying theory, the theory of Big Bang cosmology, they are denying galaxies their infancy. Given the evidence of galaxies almost as old as the universe itself, proponents of the Big Bang assume that early galaxies formed faster than initially theorized. There is no reason to assume that the history of the local universe was not punctuated by periods of sudden development. There may well have been one or more booms of galaxy formation. The universe abounds in abrupt and sudden dialectical processes. However, the attempts to adjust the birth rates of galaxies have less to do with explaining the birth of galaxies and everything to do with saving a theory that is quickly coming into question in the light of new discoveries. Big Bang cosmology, as we know, has suffered many such adjustments in its history. This cosmological theory originates from perhaps the most absurd extrapolation in the history of science. In the 1920s, the astronomer Edwin Hubble discovered that the further a galaxy is from us, the redder it appears. This reddening can be explained by referring to something known as the Doppler effect, whereby the light spectra of objects moving away from us appear redder. From this, astronomers concluded that the observable universe appears to be expanding. However, this was drawn to its extreme and absurd conclusion. If everything is moving away from everything else, at some time in the history of the universe, all matter must have been in a single point, which the defenders of the Big Bang call a singularity, no bigger than a single hydrogen atom. At that time, not only did all matter and energy come into existence, but the very fabric of space and time supposedly came into being too. But the Doppler shift is, at best, evidence of the expansion of a sector of the universe, not of a singular and absolute beginning to time and space. Here we have an unfortunate example of a fact being pushed to its absurd limit and literally making a cosmic leap. The Big Bang is not so much a matter of scientific evidence, but of the philosophical interpretation of the evidence. That a part of the universe within our narrow horizon appears to be expanding does not authorize us to affirm that the entire universe is doing so. Even less can we extrapolate from this fact that all of this results from a point of singularity where space and time mystically came into existence. Some deny that the Big Bang means a beginning to time. They claim Big Bang cosmology merely postulates that the universe existed in a hot, dense state in the past. But prominent modern cosmologists do in fact defend a beginning to time. As Stephen Hawking explained, the universe has not existed forever. Rather, the universe and time itself had a beginning in the Big Bang. The beginning of real time would have been a singularity at which the laws of physics would have broken down. Frankly, alternative Big Bang theories that attempt to avoid a singularity are no less speculative or absurd than the notion of a singularity. The astronomer who first proposed the Big Bang hypothesis in the 1920s, Georges Lemaitre, certainly had no problem with the idea that cosmic redshift somehow proves that the universe was created ex nihilo. This was because, being an ordained priest, it was obvious to him how a universe can be created from nothing. It was brought into being by God, the Creator. Lemaitre won the effusive laurels of the Vatican for this contribution to the faith. Nevertheless, it may seem impressive that this theory, first proposed in the 1920s, has survived the test of observational astronomy for a whole century. But the Big Bang theory as it exists today bears only a passing resemblance to Lemaitre's original hypothesis, precisely because of its repeated failure to tally with observational findings. The only observational success of Big Bang cosmology in the last century was a truly revolutionary discovery in 1964. Two astronomers, Robert Wilson and Arno Penzias, were using a radio telescope designed to examine satellite communications. They encountered a strange phenomenon. When they directed their telescope at any point in the sky, they found a weirdly persistent microwave signal. There was no point in the sky from which this signal did not emanate. They began to look closely at the idea that the universe had been very different in the past than it was now. This was implied by Lemaitre's idea and had been picked up in the early 1950s by two physicists, Ralph Alpher and George Gamow. Alpher and Gamow were building a model of cosmic history where the universe began in an incredibly hot, dense state. Gamow's models predicted that, approximately 300,000 years after the universe started expanding, space filled with a particular kind of electromagnetic radiation as matter particles cooled and changed their interactions. Not only that, this radiation would persist forever, a kind of fossil light. And it was this fossil light that Wilson and Penzias inadvertently picked up in their radio telescope. All the pieces of the jigsaw were perfectly slotting together. Wilson and Penzias had made an insurmountable breakthrough. The universe did indeed have a history. It had once expanded from a type of primeval atom, and it had continued to expand since. In doing so, it had left behind traceable electromagnetic emissions, which silently polluted the sky, invisibly goading desperate researchers, waiting to be found by technology that was advanced enough. This discovery, known in scientific circles as cosmic microwave background radiation, established cosmology as a science and the Big Bang theory as the foundation for all explorations of cosmic evolution. Since then, observations have further supported its veracity, and more details have bulked out the theory. Over the past 60 years, cosmology has become ever more precise in its ability to account for the best available data about the universe. But along the way, to gain such a high degree of precision, astrophysicists have had to postulate the existence of components of the universe for which we have no direct evidence. The Standard Model today holds that normal matter, the stuff that makes up people and planets and everything else we can see, constitutes only about 4% of the universe. The rest is invisible stuff called dark matter and dark energy, roughly 27% and 68%. Cosmic inflation is an example of yet another exotic adjustment made to the Standard Model. Devised in 1981 to resolve paradoxes arising from an older version of the Big Bang, the theory holds that the early universe expanded exponentially fast for a fraction of a second after the Big Bang. This theory solves certain problems but creates others. Notably, according to most versions of the theory, rather than there being one universe, ours is just one universe in a multiverse, an infinite number of universes, the others of which may be forever unobservable to us, not just in practice, but also in principle. There is nothing inherently fishy about these features of the Standard Model. Scientists often discover good indirect evidence for things that we cannot see, such as the hyperdense singularities inside a black hole. But in the wake of the Webb's confounding data about galaxy formation and the worsening problem with the Hubble constant, you can't be blamed for starting to wonder if the model is out of joint. A familiar narrative about how science works is often trotted out at this point to assuage anxieties. It goes like this. Researchers think they have a successful theory, but new data show it is flawed. Courageously rolling up their sleeves, the scientists go back to their blackboards and come up with new ideas that allow them to improve their theory by better matching the evidence. It's a story of both humility and triumph, and we scientists love to tell it. And it may be what happens in this case too. Perhaps the solution to the problems the Webb is forcing us to confront will require only that cosmologists come up with a new, dark something or other that will allow our picture of the universe to continue to match the best cosmological data. However, there is another possibility. We may be at a point where we need a radical departure from the Standard Model, one that may even require us to change how we think of the elemental components of the universe, possibly even the nature of space and time. Cosmology is not like other sciences. It's not like studying mice in a maze or watching chemicals boil in a beaker in a lab. The universe is everything there is. There's only one, and we can't look at it from the outside. You can't put it in a box on a table and run controlled experiments on it. Because it is all-encompassing, cosmology forces scientists to tackle questions about the very environment in which science operates, the nature of time, the nature of space, the nature of law-like regularity, the role of the observers doing the observations. These rarefied issues don't come up in most regular science, though one encounters similarly shadowy issues in the science of consciousness and in quantum physics. Working so close to the boundary between science and philosophy, cosmologists are continually haunted by the ghosts of basic assumptions hiding unseen in the tools we use, such as the assumption that scientific laws don't change over time. But that's precisely the sort of assumption we might have to start questioning in order to figure out what's wrong with the Standard Model. One possibility, raised by the physicist Lee Smolin and the philosopher Roberto Mangabeira Unger, is that the laws of physics can evolve and change over time. Different laws might even compete for effectiveness. An even more radical possibility, discussed by the physicist John Wheeler, is that every act of observation influences the future and even the past history of the universe. It is not obvious, to say the least, how such revolutionary reconsiderations of our science might help us better understand the cosmological data that is flummoxing us. It would necessarily be a leap of faith to step back and rethink such fundamentals about our science. But a revolution may end up being the best path to progress. That has certainly been the case in the past with scientific breakthroughs like Copernicus's heliocentrism, Darwin's theory of evolution, and Einstein's relativity. All three of those theories also ended up having enormous cultural influence, threatening our sense of our special place in the cosmos, challenging our intuition that we were fundamentally different than other animals, upending our faith in common-sense ideas about the flow of time. Any scientific revolution of the sort we're imagining would presumably have comparable reverberations in our understanding of ourselves. As Geraint F. Lewis, professor of astrophysics at the Sydney Institute for Astronomy, part of the University of Sydney's School of Physics, said, "Sometimes, a new idea completely overturns the way we look at the cosmos." Einstein, Lemaitre, Friedman, Hubble, and others showed that our universe is not static, but expanding. Throughout the 20th century, astronomers mapped out our location among the stars of our galaxy and our galaxy's place in the cosmos. Maybe we've got the picture roughly correct, or maybe we're just waiting for the next Newton or Einstein to show us an even grander picture of the physical universe. To do this, we also need new instruments. Luckily, astronomy has a bright future. We are about to have the Habitable Worlds Observatory, a Hubble Space Telescope on steroids that will see Earth like exoplanets around Sun like stars. We are about to have a Far Infrared Observatory, the Origins Space Telescope, to detect molecules in cold, dusty objects and see stars and planets forming. And one day, we will have the Lynx X-ray Observatory, to understand extreme temperatures around black holes and explosions of all sorts. In addition to new telescopes, we have new computing tools. We can already make movies of the history of the universe based on hypothetical initial conditions and the laws of physics, just as we can predict the weather with hydrodynamic codes. These simulations are limited. As objects evolve and become smaller and hotter, the computation to describe them becomes too difficult to include in the original simulations. But AI may allow us to overcome this by reducing the computation necessary to get good results. Jumping ahead, I see no law of nature preventing artificial general intelligence, a form of AI that truly understands the words it uses to talk with us. Given the billions of dollars being spent every year and the immense motivations leading to those budgets, I think it's only a matter of time. We don't have to understand how it works to use it. We don't understand the human mind either. Be ready to be amazed. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.